Hi, and welcome to Module 3 of Lecture 3. In this module, we're going to continue some mathematical foundations focusing on matrices. We're going to highlight just a few major points about matrices, some definitions, some manipulations you can do with them, and mostly why we care about them in the first place in the context of multiple regression. As before, there are more elaborate videos you can watch on the Math Camp, on the math videos. You can get on the same YouTube channel here. These are on Lecture 10 for matrices. Okay, let's start with some notation involving matrices, and a lot of this will be very familiar from when we talked about vectors. When we talked about vectors, to remind you, we had a definition where we had elements of a vector, and a column vector, some v, equaled, say, a1, a2, I don't know why I used v and a, dot, 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 down to some an. This was a vector, and each one of these was elements of a vector. And we dealt with vectors by treating them element by element. So if we wanted to add two vectors, we added the corresponding elements of each vector. If we wanted to multiply by a number, we multiplied that number by each element of the vector. Okay, so those are vectors. And they were useful, we said, because we could put them independent variables in them. So if we had x and there were n data points of our independent variable x, we could have an n-dimensional vector, a vector of length n, that captured and held all of our data for the independent variable x. That was useful. Well, we can do the same thing now that we have more than one independent variable. So let's say we have multiple independent variables. We have an x1, and we have an x2, and an x3, and forget the constant for now. And let's say you want to put them all together and hold them in some fashion. Well, what if we just stack all of our vectors together? So let's say x1, so this is the first data point of x1, and this is the second data point of x1, and this is the third data point of x1, and so on down to the nth data point of x1. So we have here is the same vectors before. We've changed notation slightly so that the second one corresponds to the independent variable we care about, x1 in this case, and the first index, the 1, 2, 3 down to n, corresponds to the data point, which data point we're looking at the moment. So the first index in the subscript in x over here is the same as the subscripts in this vector over here. The second subscript corresponds to which variable we care about. Okay, so what if we stack them? So the next one is going to look kind of the same. There'll be a 1 because it's the first data point, but now it's the second variable. And we do that downward here, all the way down to xn2. Then do the same thing for 3. And I'll skip more things here and go down to the bottom of xn3. I put them all together, and we have 3 columns and n rows. This thing we call a matrix. It is some matrix corresponding to that captures all of our independent variables and all of the data stored in the independent variables. We could write this as capital X, which equals this. And we drop, so for a vector, we often had a little, it's either in bold or we had a little vector. For the matrix, we just typically use a capital letter. Sometimes we can use a bold letter, but a capital letter to indicate this is a matrix. Usually you can tell by context. Okay, so here's our matrix. How is this useful? Well, it's a way, as a first pass utility, it's a way of storing all of our data for all of our independent variables in our multiple regression. We can do the same thing with so if you wanted to use the same notation from before, where we had independent variable x and a control z and a constant, the first column would be the constant, and I'm just making 4 data points to make my life a little easier. The second one would be the x, and the third one would be z. The only difference between this and what I just wrote is that I'm referring to all the independent variables by a subscript, x1, x2, x3, and rather than using separate x's and z's and such. But the same thing, the point is you put all of your independent variables in as columns in your matrix, and you form a matrix from these vectors of independent variables by shoving them together. And you want here to use column vectors put together for your independent variables to use the standard form here. Matrices have many other uses, but this is the one we care about here for the context of this course, so I'm just going to stop here and focusing only on that. So, before we go further, we need some definitions. A diagonal matrix is a matrix that only has elements on the diagonal. The diagonal has the same subscript in both positions. So x11 is the element of the diagonal, x22 as well, and x33 and so on. This thing is a non-diagonal matrix. We can write, so often we write the row and column number as subscripts to the main matrix. This thing is an n by 3 dimensional matrix. So it has n rows and 3 columns. A matrix that has a square matrix, we say, has equal numbers of rows and columns and would look like this. Usually, in storing our independent variables, we do not have a square matrix because we have many more data points than parameters. So typically we have something that looks like this, n by m, where n is the number of rows or data points, and m is the number of parameters. If you want to use k instead of m, they mean the same thing. They're just an index for the number of parameters. So, but if you have the same number of rows and columns, you have a square matrix, then every element in the diagonal is an element that has the same position in the row and the column. So x11, x22, x33, and so on. The identity matrix is always square, and for an n-dimensional identity matrix, we have 1s on the diagonal, and 0s in every other position. As we'll see in a second, it's an identity matrix because when you multiply a matrix times the identity, you get back the matrix again. A symmetric matrix is one in which all of the elements ij are the exact same as the elements ji. The identity is symmetric because everything ij is 0 when I doesn't equal j, and everything ji is 0, so 0 equals 0. In general, a matrix would be symmetric if you have, like, say, some diagonals. I'll do a 3 by 3 one. And then you have, let's say, an A, B, and a C over here. And then, because this is x21, this is x12, so it's the same. And then this is x31, so x13 is the same. And this is x32, and this is x23, which is the same. This is a symmetric matrix because all the first position, all xij's rather equal all xji's. This is a symmetric matrix. And finally, the transpose of the matrix is the matrix you get, and it's written like this, sometimes x transpose usually. And it's the matrix you get by flipping all the xij's for all the xji's. So diagonals stay the same, and then all the ij's become ji's and vice versa. So that looks like this. If it were symmetric, I'll just do a 2 by 2 here because they're easier for me. x11, x22, x12, x22, and if you transpose that, then that's going to equal x11, x22, x2, so this is a 1, not a 2, x21, x12. So that's the transpose of that matrix. It's a little more complex if you take a transpose of a non-square matrix. Let's take this x over here. This x that's n by 3. Well, what's the transpose of that? Actually, let's do the transpose of this x because it'll be more easily identifiable on the screen. So if we take the transpose of that, we're still doing the same thing. We're taking all the xij's and making them xji's. So in this case, there's 4 so for column 1, so x11, x21, x31, x41, we're flipping them the other way. So those ones become x11, x12, x13, and x14. So now the first row of this thing looks like this. Because whereas before they were x11, x21, x31, x41, now they're 1, 1, 1, 2, 1, 3, and 1, 4. And that's the same thing for the second column. And it's the same thing for the last third column. So this matrix is going to be a matrix that is m rows and n columns. So because we're flipping rows and columns, we flip the size of the dimensionality of the rows and columns as well. So now we have a 3 by 4 matrix instead of a 4 by 3 matrix. And that's the transpose. If you wanted to see one more example of that, the transpose of this one would be a 3 by n matrix, which would equal x11, let's write over this because x21 dot 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 x n1, and the second row is x what am I doing here? X2, yeah, x12, x22 dot 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 xn2, and the third row is x13, x23 dot 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 and xn3. So diagonal elements stay where they are, everything else flips, and you get a matrix. Before it might have been a matrix that was very long, many rows, but narrow with only 3 columns. Now you have a matrix that has only 3 columns, so it's not 3 rows, so it's not very long anymore, but it has n columns. That's the transpose. Okay, that's a bunch of definitions. I'm going to give you a few more because they're necessary before we go on to the sort of main point of all this. Okay, so we have definitions for addition and scalar multiplication. It's the same kind of logic as for vectors. So to add 2 matrices, you can add any 2 matrices that have the exact number of rows and columns. So if you have 2 by 2, you can add any other 2 by 2 matrix, and you add it element by element. So this would be A11 plus B11, and A22 plus B22, and A21 plus B21, and A12 plus B12. That's how you add matrices. It's element by element. If you don't have matrices with equal numbers of elements, you can't add them. Okay, scalar multiplication is similar. If I have some constant c, that's just a scalar, and I multiply it by my a, which is 2 by 2, then I'm going to end up with c multiplying each element. So it'll be CA11, CA12, CA21, and CA22. So that's it. So addition and scalar multiplication work the same way they did for vectors, and they're pretty straightforward. However, just like for vector multiplication, which there are many varieties, and we considered one, the scalar or dot product, there are matrix multiplication also has different varieties. The most common one that we can deal with all the time is also more complex. So first, I'm not going to go into all the details here, but the idea is this. If I have an n by m matrix, I can multiply that by any matrix that has m rows and, say, L columns. So importantly, if I multiply A times B, and I'll put a little X there, the number of columns of the first one I'm multiplying by has to be the same as the number of rows of the second one. If I don't have that, I can't multiply the 2 matrices. So because of that as well, AB is not the same as BA in general. A times B will not equal B times A as a general rule. Matrix multiplication is not commutative, unlike scalar multiplication. Right? If I have 2 numbers, A times B, they also equal B times A. If A and B are matrices, they do not equal B times A in general. There's all sorts of consequences, but for here, just to be aware that that's the case. To multiply 2 matrices, the first one you multiply on the left has to have the same number of columns as the second one has rows. We often call things left multiplication and right multiplication to distinguish multiplying a by a on the left to multiplying by a on the right from multiplying by a on the right. These are different things. Okay. If you do have two matrices of which they have the same number of columns and rows in that order, then you can multiply them. And the way you do that, and a nice way to do that, I'll do a 2x2 version just to give you a sense of how this works, and I'll stop there. The more general formula you can get in the other videos or online, anywhere you want. Let's use square matrices for the moment, just for the first example. And I'll show you a non-square one after that. Okay, the way to do it is to take the first row here and kind of rotate it in your head and multiply it by the first column. That's the first element. So the first element of this new matrix is going to be A11 times B11 plus A12 times B21. So you might remember what the dot product definition was. This is effectively the dot product of the first row and the first column. Then the second time, to get the second one, you multiply the second row times the first column. That gives you the element in the multiplied matrix corresponding to the second row and first column. So now I have A21 and B11 plus A22 times B21. I can do the same thing for the last two. I won't do it. You can do it at home if you like. But that's the idea. You basically take the dot product of each row times a corresponding column of the first matrix times a corresponding column of the second matrix, and you figure out where they go. The row of the first matrix, the row of the vector in the first matrix determines what row you're in the multiplied matrix, and the column of the vector in the second matrix determines where you are in the multiplied matrix. I'll do one more to make this a little more complicated to show you how that works in more detail. So let's say I have, I'll have two rows, but three columns of this one. And then I have to have three columns of this one, and I'll make it two rows so I don't have to do too much actual stuff. So now I have, three columns of this one, but only two rows. No, sorry, I need three rows of this. I apologize. Let me fix this. Okay, so now I need three columns of this one. Sorry, three rows of this one. I keep saying columns. I apologize. So I need the same number of rows of the second one as I need columns of the first one. I have three columns of the first one, so I need three rows of the second one. There we go. Now, I'm going to go through and do this one. I need more space because the things will be long. I'm going to take the first row of the left matrix and multiply it by the first column of the second matrix. That gives me A11 times B11 plus A12 times B21 plus A13 times B31. I should have left my room here, so I'm going to erase this. Other side. Okay. Okay. Note, if you get confused on what goes with what, every time the column index of the first scalar here, the first element of A, has to match the row index of the second element. So 1, 2 matches 2, 1, 1, 3 matches 3, 1. This is the first row and first column. And if you're confused where they go, the row index, which should be constant through all your things here of the A elements, tells you which row you're in, and the column element of the second matrix, the B matrix, which should be constant through all these, tells you what column you're in. So that's 1. The next one is going to be the second row down here times the first column. That gives me A21 B11 plus A22 B21 plus A23 B3, 1. Again, all the column of the A matches the row of the B for all of them, going 1, 2, 3. And then the index on the row for A is 2 for all these, indicating you're in the second row. The column for the second one is still 1, so we're still in the first column. Now we do the same thing over here. We take the first row again, but multiply by the second column. So now we have A11, B12, plus A12, B22, plus A13, B32. And we do the same thing down here. We do, to finish up, we do A21, B12, plus A22, B22, plus A23, B32, and then we finished it off, which I ran room for. But you get the point. Actually, I think I can go off the thing, can't I? I can. Okay, so what we get is a 2 by 2 matrix. So whenever you multiply A, which is n by m, times a B, which is m by l, you're going to end up with some C, which is going to be n by l. That's always true. So that's how you do it. It takes a little getting used to. Everyone has different ways of remembering this. I personally like the sort of visual way of sort of visually grabbing a row of the first matrix, rotating it, and multiplying it by row of the second, by column of the second matrix, and doing that for each element. You can do it however you like. People have different preferences here. But remember, if you keep track, the biggest problem people have with matrix stuff is just not keeping track of what element goes where. If you keep track of all the elements carefully, you'll find that it's not as onerous as it might seem on first glance. Okay. So this is matrix multiplication. The other stuff I'm going to show a little less detail because it's not quite as important at this stage. Oh, I just want to do this. Okay. Determinants. One often thing we're going to want to avoid in doing statistical analysis and multiple regression is having two independent variables that are too highly correlated with each other. When you have that, we have something called multicollinearity, and that's problematic, and your regression will fail. Here's what it looks like. If I have, say, x1, 1, and x2, 1, x3, 1, and so on down to xn1, I have another variable x2 that looks like this, right? If it's the case that x1 equals 2 times x2 for all data points, so they're perfectly correlated, one's just twice the other one, what's going to happen is my regression is going to fail. I don't need effectively the second independent variable because its variation is identical to the variation of the first independent variable. And the problem, you can kind of think of it conceptually from what we talked about before. If I'm looking at the variation in y with respect to x, holding other things constant, how do I do that if I'm holding something else constant that's the same as the first thing? Right? That shouldn't work. There's more to it than that, but I'm going to stop. But I think that's a reasonable way of looking at it. If I'm holding if I'm holding the variation if I'm calculating the variation of y with x, holding every other thing constant, if I have a second x that's the same as the first, how do I hold it constant if it's the same? If its variation is the same? So we can't run regressions like that. There's a nice way of looking at that, and one way of seeing that is that the determinant is too close to 0. The determinant of a matrix, and I'm not going to give you the general formula. You can look at that on the other math camp if you like to, or any Wikipedia for that matter. But I'll do it for 2 by 2. Here's a 2 by 2 matrix, A, B, C, D. The determinant of this is often represented by vertical lines around the matrix, or if this is A, it would be vertical lines around A, and it's AD minus BC. So it's the diagonal elements multiplied together minus the off-diagonal elements. The general version of this is a little more complex and involves breaking down larger matrices and doing this kind of thing for each element one by one, and then breaking down the smaller and smaller to get 2 by 2s. Again, you can see that elsewhere. It's not so important right now. But this is what it is in this case. If this thing ends up being 0, we have what is called a singular matrix. So if this equals 0, we have a singular matrix. If your independent variable matrix is singular, you have problems. So it's a nice, easy way to tell that. More generally, for what we're going to do is we're going to be calculating inverses which require the determinant. The inverse of a matrix, A inverse, is the matrix such that if you multiply it by A, either on the left or on the right, you will get back the identity matrix. So just like the inverse of multiplication is division, right? If I multiply by 1 over 3, if I multiply 3 by 1 over 3, I get 1. It doesn't matter which direction I multiply it by. The inverse of a matrix is the matrix that, when multiplied by the original matrix, gives you back the identity matrix, which is 1 in the context of matrices. You can calculate it using the determinant in the original matrix. For 2 by 2, it's equal to, so A inverse here would be 1 over AD minus BC times DA, and then subtract, and then you have minus BC. And you can check this, which is good for me because you always mess up doing this kind of thing on the fly. If you multiply, let's say, A times A inverse, then you get out front 1 over AD minus BC, and then these two matrices, AB times C, ABCD times D negative B negative C A. Now I'm going to multiply these two by these two, right? The first row times the first column. So the first element is going to be AD plus BC, because there's a minus here. Sorry, that's not plus. What am I talking about? Minus BC. Minus BC. So AD minus BC in the first one. And the second one, I'm going to take the first row times the second column for this element. That's negative AB plus AB. So that's going to cancel to 0. In this one, I'm going to take the second row times the first column, which gives me CD minus CD. That cancels to 0. And the last one is the second row times the second column, which is negative BC, so negative, plus AD. These are 0. These, when divided, I forgot this part, AD minus BC. These are the same as these. So this gives me 1, 1, 0, 0, and I have identity back again. So this is the inverse of A. For bigger matrices, it's more complex. But again, by and large, you're not going to be calculating any of this stuff yourself. I shouldn't say again, I've said it before. By and large, you're never going to be calculating this stuff yourself. You're going to be using computers to do most of the stuff for you, but it's useful to know what they're doing. So those are inverses and determinants. I'm going to finish this up by talking about the most important part, the use in OLS. I glossed over completely how to compute the coefficients in OLS. It turns out, and you can see that proved if you look at those math videos, that the coefficient for beta is a vector. This is a vector, and it's going to be equal to x transpose x inverse. So I take the transpose of my matrix x, multiply it by the original x. This is the independent variable matrix. That will give me a matrix. I take the inverse of that, I multiply it by the transpose of x, and I multiply it by my vector of independent variables y. That gives me my vector of coefficients beta hat. So this is a way you can calculate by hand all the coefficients on your multiple regression should you want to. And that's it. So I should say a singular matrix, I should have mentioned that, a singular matrix will not have an inverse, which is one reason why this fails. If I have a singular matrix, so the determinant is close to 0, is 0 or close to 0 in computers. If it's 0, then this thing doesn't exist. So if this thing is singular, if x transpose x is singular, which will happen when you have two identical columns in your original independent variable matrix, if this thing is singular, so there's a determinant of 0, this thing doesn't exist, and I can't find my coefficient vector. What this will do is produce a vector beta in which the first element, beta 1, which is the coefficient on your first independent variable, beta 2, and so on down to m, which is the coefficient on your mth independent variable. So that produces this. And to show that it works out correctly, if X is an n by m matrix, then X transpose X is going to be X m times n, which is X transpose, times X n by m. That equals an X m by m matrix, so it's the size now of the number of parameters you have. The inverse is the same size. So now I'm multiplying X transpose X inverse, which is m by m, times X transpose, which is m by n. That gets us a matrix that's m by n again. And multiply that by a matrix Y, because vectors are just matrices with only one column, by effectively a matrix that has one column and n rows. So now we get m by m times m by n gives us m by n. M by n gives us times n by 1 gives us m by 1. This beta here is effectively a matrix with m rows and one column, and that's what you get. One row for every coefficient on every independent variable, and that gives you the coefficients on your multiple regression, and that's why the stuff is used in multiple regression and the stats that we've done so far. Okay, that is it for now. It's pretty long, but hopefully this was useful both now for this course and for future stuff you do in research design and social sciences or data science or whatever. Thank you very much.